So thank you for having me here today, Michelle. This is good? Okay, cool. So I'm going to be talking today about spooky space weather and the Halloween storm. And because I'm learning Irish at the moment, that is Spá Samse Scamrol agus Storm Ihasawa, I think. Yeah, I got a thumbs up. I will take corrections on my Irish later on. So I just like to talk a little bit about the background of myself and Dunsink Observatory in case you're not familiar with it. So this here is Dunsink Observatory. It was built in 1785. It's a purpose-built observatory. Nowadays, it's mostly computational lab. So that means we do most of our research, data analysis, on the computer. So you can, if you scan the QR code, that'll take you to our webpage. You can follow us on social media, obviously, as well as the DIAS channels as well. So a few cool things about Dunsink. So the Dublin Meridian runs through Dunsink. So it runs through, there's a room at the back of this building on the other side. The Dublin Meridian runs through there. So that used to be 25 minutes and about 20 seconds off Greenwich. That changed in 1916, and we match London now. Our third director, William Rowan Hamilton, invented quaternions. We say invented, discovered. So he used to go for a daily walk. He lived here at the observatory. He went for a walk down the canal every day, and he had this flash of inspiration, and he scratched it on Broom Bridge. If you know Broom Bridge near Ashtown, and this is the plaque on Broom Bridge there. So he lived and died peacefully in this building. Finally, ourselves, Dunsink Observatory, Armagh in the north, and Burr are working together at the moment towards UNESCO World Heritage status. So this is a very important building in the history of astronomy in Ireland and also worldwide astronomy, particularly relating to quaternions. So yeah, absolutely, come out and see us. You can find information about our open nights on our webpage. If you don't get the QR code, you can just Google DIAS or DIAS Dunsink, and you should get there. So before we start talking about the Halloween storm, specifically, I'm going to talk more generally about solar system space weather. So let's set ourselves up in the solar system. So when you were a child, how many planets were there versus how? Sorry? 9, exactly right. Nowadays, I'm afraid there's only 8. So does anybody know why Pluto is no longer considered a planet? It's not moons. It doesn't clear its orbit. Well done. Okay, so there's 3 things you've got to do to be a planet. You have to orbit a star. Pluto's doing that. It's orbiting the sun and green. You have to have large enough gravity that you are roughly spherical. Which Pluto does, but it does not clear its orbit. So all the other planets, well, the planets of the solar system, all the other bodies listed here, have cleared their orbit. That means they've either absorbed all the other pieces of rock in their orbit or ejected them. But Pluto hasn't. So Pluto is like the M50 at rush hour. Pluto's orbit it's really busy. And there's actually another body in Pluto's orbit that's bigger than Pluto. So that's why Pluto is no longer a planet. It was demoted in 2006. When I was a child, it was a planet. The kids that come to the observatory nowadays, they don't think it's a planet. They're like, there's 8. So different to their parents. So it's quite a talking point. So the sun holds over 99.9% of the mass of the solar system. And the sun is a big ball of plasma. So plasma is a fluid that's made up of ions and electrons. The sun's really, really dense. And it's a sort of a fundamental fact proved actually before the space age that the sun's atmosphere is flowing continuously out into the solar system, and we call this the solar wind. So the solar wind is that plasma, again, filling the solar system. It impacts all of these planets, and it's carrying the sun's magnetic field. They're stuck together like the plasma was a jelly, and you have like a string or a hair running through it as the magnetic field. So the term space weather is kind of an umbrella term. So it describes the effects that the sun has on the planets of the solar system, but especially the sun's effects on Earth. So generally when people say space weather, they're talking about Earth, but we also have space weather at other planets too. So space weather is not the same as rain, wind, and storms that you get your umbrella out for, but we are often borrowing those terms. So often we're borrowing them in kind of an incorrect way to weather scientists, but it'll be, you know, solar wind or geomagnetic storm, and it's completely different to the storms that you know that we experience here when the weather's bad. So space weather is different on the planets depending on what their magnetic field is like. So here we've got the planets of the solar system from the sun will be, you know, not to scale all the way off here, all the way out to Neptune. And what I've got here is I put a little magnet where they have a magnetic field. So if we start at the Earth, everybody in this room intuitively knew before this talk started that the Earth has a magnetic field, because that's how your compass works. That's how birds navigate. One of the ways birds navigate when they're migrating is something that as beings and as a planet, we have always sort of known about. Now we measure it, we understand it much better. But yeah, so the Earth has an intrinsically generated magnetic field. So does Mercury, it's much smaller. So does Jupiter, it's much, much, much bigger. Saturn, Uranus, and Neptune. So Uranus is very different angle. So Uranus's magnetic pole is almost completely pointing at the sun. Mars here, I've got 3 tiny, teeny little magnets because Mars doesn't have a global magnetic field. So your compass isn't going to point like it does on Earth. It has lots of small patches of what we call crustal magnetic field. So it used to have a global magnetic field, it cooled down, and now it's got lots of tiny, teeny little magnetic fields. And then Venus, no magnetic field. So Venus's interaction with the sun is unique of all these planets. So in terms of thinking about space weather, can't see this so good on here, so I think you can see it on the TV there. But this is a graphic made by the European Space Agency. So I put European Space Agency there. I know not everybody's heard of it. So everyone in the room's heard of NASA. NASA landed on the moon. They're very famous. The European Space Agency is what your taxes are paying for, okay? So this is, they're doing very similar things, but this is what our taxes are paying for. So they made this graphic, and this highlights some of the key space weather effects. So there's a whole bunch of different things that can happen. So it can knock out our communications, it can overload our power lines, it can delay your train, it can ground your plane, it can be an issue for astronauts in space, all kinds of things like that. And we have really particular events where if you have, you know, really bad space weather and you've lost mobile phones, you've lost all these things because of, say, an earthquake, and then you have really bad space weather, you lose HF communications, no communications at all. That's all of your communications gone. So this is a really important natural hazard that governments are starting to prepare for. So the Irish government, it was last year, summer of 2023, that it became listed on our national risk assessment. So it's something that the government is thinking about and hopefully preparing for. So in terms of the risk to your personal health, it's not getting down to the ground. It's a risk to our technology, which then has impacts on the economy and travel and communication and all these things. So let's go back to what's causing the space weather, and we're back on this screen now. So here we have a coronagraph, so we're looking at the sun. The sun itself is blocked out in the middle because it's very, very bright, and we want to look at the sun's atmosphere. So as I said, it's streaming out continuously into the solar system, but you can see it's really variable. So this here is the solar wind. You can see we have this big puff that we call a coronal mass ejection, but it's coming out in all directions all the time. And it's really variable. It can be slow, it can be fast, it can be dense, it can be sparse. And around the Earth's orbit, it's traveling about 400 kilometers a second. And so just to put that into context, our motorway speed is 120 kilometers per hour. That is 0.03 kilometers per second. So much, 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 much slower. Does anybody know the fastest plane in the world? No? So does someone say? No, well, I don't know if it's a fighter jet, but the fastest plane in the world is the Lockheed Blackbird, and that's still less than 1 kilometer a second. So that's still 400 times slower than the solar wind. And this 400 kilometers a second, that is your boring, everyday solar wind. So this is really, really fast, is the point that I'm trying to make. So The big puff that I described before is a coronal mass ejection. So here we're looking much more closely at the sun. You can see you're getting this loop of plasma. So again, that's that fluid, ions and electrons. And eventually it's going to spit out. And what we're talking about is one of the most dramatic events. So these are plasma eruptions from the sun. We're talking about billions of tons of material and a really high magnetic field coming out of the sun. And it can take up to a few days to reach the Earth. So light from the sun gets to the Earth in 8 minutes. So if the sun switches off, we find out in 8 minutes. But this matter, these billions of tons of material, is taking up to a couple of days to get to the Earth. And this is one of the most dangerous solar phenomena. This is what's causing our really dramatic, really dangerous, life-changing space weather. And this is just an image to show you, here's a coronal mass ejection. We've zoomed in on the sun, and here's the tiny little dot which has us to scale. So you can see when this coronal mass ejection is coming past, it is hitting the entire Earth. We are being, well, not swept away, but we are being overcome by this plasma coming from the sun. It's a huge, huge event. So what happens at the Earth? We're going to talk a bit about Earth's storms. So again, this is not your storm that we had the other week that blew down a bunch of trees. This is a geomagnetic storm. So we go back to the Earth's magnetic field. So here we have the Earth, and as I said, you all knew before tonight, that the Earth had a magnetic field, even if you didn't know that you knew. Here's the Earth, and essentially the Earth's magnetic field, if it was the only thing in space, would be like the magnetic field of a bar magnet. So here's the magnetic field of a bar magnet. You might remember that from school when you put the bar magnet under glass, and with the iron filings, it's going to trace out these lines. These are magnetic field lines. So the Earth's magnetic field has a south magnetic pole in the geographic North Pole. So you can see here the magnet's upside down. And it's also tilted from the spin axis. So when the Earth, if I am the Earth and I'm spinning, the magnetic field is kind of like that. And that creates the magnetic field is going like this. So it creates these oscillations, which mean that we have seasonal changes in our space weather. So the reason we have a magnetic field is that Earth's core is molten. It's made of a molten metal mixture, mostly nickel and iron, that's moving around, and it's a really fundamental sort of physics effect that if you have a moving conductor, then you get a magnetic field. So this creates our intrinsic planetary magnetic field. That's similar to other planets of the solar system, generally speaking. The actual generation of planetary dynamos is something that's outside of the scope of my field, but it's not very, very well understood yet. But generally speaking, if you have a moving conductor, so a liquid metal in the middle, then you're going to get a magnetic field, and that's what we have at the Earth. So the Earth's magnetic field is an obstacle to the solar wind. So this is not to scale, as you can see, they're much, much further apart. Here's the sun, here's the solar wind coming out, and here's the Earth's magnetic field. So I've got this little picture in the corner here that you can see. So if you imagine a rock in the river and along comes the water encounters the rock and it has to go around. And you can also imagine if you had that big wave, the coronal mass ejection, it really buffets the rock, but it has to go around. And that's the same in this case. So the solar wind is a fluid and the magnetic field is an obstacle. So the solar wind you see these streamlines here, it has to go around. But what it does is the magnetic field deforms a bit more than a rock would. It gets squished on the side facing the sun, and it gets really long and elongated on the other side. So you end up with this kind of bullet shape that actually goes on maybe 1,000 times this size here. It goes a really, really long way. And we call this region of space the Earth's magnetosphere. So that's the sphere of space, although it's not a sphere shape, that is dominated by the Earth's magnetic field. So, as I said, the solar wind is coming out all the time, it's constantly buffeting the Earth's magnetosphere, and it's controlling the size of this region of space. So when the solar wind pressure is higher, as with a balloon, the magnetosphere shrinks. So that's like when the balloon is low in the atmosphere, the pressure is high, the balloon is small. As the balloon rises up to the low pressure atmosphere, it gets bigger. And the same is true, except, you know, it's coming from the left, if you will, rather than being moving up and down in the atmosphere. So high pressure, we get a small magnetosphere. Low pressure, big magnetosphere. And what happens when the pressure changes is it can change really rapidly, and it's like punching a jelly. Everything inside the magnetosphere will wobble, and that will cause really interesting effects that we study. So this is a kind of complicated video, but I'm going to try and explain it. So this is a simulation of a Carrington level event. So this is the largest, the Carrington event is what we think is the largest geomagnetic storm that has ever happened. It was in the 1800s, so we don't have pictures so much, but I'll show you some stuff in a bit. So what we're going to simulate here is a coronal mass ejection, so that big puff from the sun impacting the Earth. So what I've pointed out here is you can see the Earth's magnetic field. You can see roughly where it's ending about here before CME. And then if I click, we're going to see in comes the solar wind, and you can see how much it's shrunk. The magnetosphere has actually been almost completely eroded by the CME in this case. So what we've had is the CME significantly compress. I'll see if I can play it again. Compress the magnetosphere, shrinking it a huge, huge amount, and really buffeting the magnetic field. So here we have the Carrington storm. I did say I was going to come back to this. So this is the strongest geomagnetic storm ever recorded. If that happened today, you would know about it. We would lose satellites. We would lose all kinds of technology. It was huge. So this was observed by someone called Richard Carrington, hence the name, in 1859. And so there was some controversy because he was an amateur astronomer, and in the ways of sort of snobbiness back then, some of the scientists didn't believe him because they didn't see it themselves. But nowadays we accept his results because there's so much other evidence from the time, and it all adds together nicely. So he was looking at not directly at the sun. Obviously we don't do that. You can project the sun onto a piece of paper if you have good instruments. And he saw sunspots, which are these dark black spots here, and he sketched them. And then this is an actual image of the sun, not from 1859, where someone has taken this sketch and stuck it to scale on the sun. So you can see how big those dark black spots are. And this here is a different sunspot, which we've actually observed with cameras, just to show, you know, this is a really big one that we've seen, and this is the size of the Carrington storm. So what is a sunspot? It's a dark area of dense magnetic field, and it's often where these dramatic events are coming from. It's actually one of our longest term data sets of observations in any field, because it's something that particularly astronomers in Asia have been recording for many, many centuries. So we can see what the sun's been doing for all that time. But anyway, so this is the strongest geomagnetic storm since records began, if you will. So what else did we see? So there were gold miners sleeping in their tents, and the aurora, the northern lights, was so bright that it woke them up. We saw aurora at really low latitudes in Hawaii, Japan, Colombia. So aurora are generally seen at really high latitudes, so at least 60 degrees latitude in, you know, Scandinavia or Iceland, places like that, high latitude places. And most significantly, in terms of practical space weather effects, this was one of the first times that we have this recorded that currents were generated in telegraph lines. So they were able to talk to each other with the power off because the space weather was making the power. And in fact, sparks hit operators, and there were some fires as well. So that's one of the first times we can say, okay, space weather affects our technology. So moving forward slightly in time, and we will get to the Halloween storm, we're going to talk next about the Quebec storm. So I'm calling this the Quebec storm because it caused a large-scale outage in Quebec. But here you can see, again, we're looking at sunspots, those dark patches on the sun. And each one of these images is another day. So it's taking a picture of the sun from this observatory in Arizona, and you can see the sunspot being tracked across different days. So we're going from the 7th of March to the 17th of March in 1989. Then we are just about in the space age here in 1989, the space age in terms of my field. And I've tried to match this auroral image to a Google Maps here. So you can see this is the band of the auroral oval. So the auroral oval is a ring, it's a donut around the Earth's magnetic pole. And there's a tiny little arrow here and a tiny little arrow here. And this is where I think they are. Obviously, this is quite an old paper, so the documentation is not as good as we are forced to do these days. So you can see, I think Chicago is around here, and then this is Canada. So the key point here is we're at a low latitude again. It's very, very bright, and it's very, very thick in this direction. And this storm is particularly famous because it overloaded the transformers in the Hydro-Quebec system, and that led to a blackout for 9 hours. Now, here we have a map of North America, and every one of these dots is a power system anomaly, which is kind of a vague term, but that's what it's been described of. It can be, extra current generated in the system. It could be overloading, and things like that. So what else did we see? Well, as I described earlier, high-frequency communication is something that can be affected. So high-frequency communication is the most reliable method of communication for the military. It doesn't matter where you are on the planet, you can do high-frequency communication because it's bouncing off the ionosphere, and broadly speaking, the ionosphere is most often there. Of course, when there are issues with high-frequency communication, we don't really find out about it because the military don't tend to tell us. But in this storm, Australian UN peacekeepers reported that they lost communication. I'm sure it happened to other militaries as well, but they just didn't tell us. So there were interference in the power systems, you can see from this map. Satellites lost control, some of them were got back. But what's important is, these satellites are millions, if not billions of euros of investment, so losing control of them is quite a big deal. And the 9-hour blackout across Quebec cost $20 million. And then finally, this is actually a different event, but I think it was kind of fun to point out, there was a similar event a few months later in 1989, and that actually halted the stock exchange. So we're talking about real life impacts on your life, your pocket, your texting your mate these days, not in 1989. That's actually, that's going to affect your life. It's not going to affect your personal health, but it is going to be noticeable. So moving on, again, as I said, I'm learning Irish, so we have Taoiseach and Down Ala here, Down Ala even. And we're going to talk about the Halloween storm, because it's the Samhain festival. So what caused a Halloween storm? So now we're talking about 2003, we have many, many observations. And this is a really huge event, the Halloween storm. So you may remember we had some aurora in May. That was the biggest storm since this storm. So this is still the biggest storm in the space age, I think. So again, we have a coronagraph here. So again, we're looking at the sun. It's been blacked out in the middle, and they've actually stuck another green image on it. And then we've got a square here, and then another square. That's two instruments stuck together. So what you can see is the solar wind is coming out in all directions. This bright thing here is Mercury, so we can pretty much ignore Mercury. What you can see is it's coming out and it's very variable, and sometimes it's really bright. And sometimes it completely overloads the detector and just goes white. So when it's overloading the detector, that means the particles are actually impacting the detector directly and coming straight past, and the detector's just like, whoa, I can't see anything. It's like shining a torch into your eye from this distance. So you can see there's lots of different things happening, and we actually had several events, several things come out the sun back to back. So it's often actually described as the Halloween active period of a few days, or something like that, but Halloween storm is a lot more catchy. So like I said, this is the largest solar flare ever recorded in 2003. It's not necessarily the largest to happen, but it's the largest one we've recorded. So 2003, we're entering the era of space weather preparedness. So preparedness is when we're talking about preparing for all these natural hazards that happen, so space weather, earthquakes, and things like that. Some societies are more risk averse. Our part of the world less so, because we're not so used to natural disasters. But for example, New Zealand, they're very used to it, so they are much more hot on space weather preparedness than we are. So because we're in 2003, we have these space advisory bulletins, and this is an example of them. So solar active region produces intense solar flare. And who's reading that? Well, governments are reading that, airlines are reading that. Nowadays, I'd hope that train operators are reading it, and the stock exchanges are reading it, people like that. Anyone that's interested in the risk to technology. So some other things that happened. So here you can see my map of the world here. We had a grid breakers trip in North America. We had a power cut for 50,000 people in Sweden. And 12 transformers were overloaded in South Africa. And what's interesting about that is if you look, South Africa is kind of what we would describe mid-latitude, as mid-latitude in terms of the magnetosphere. And what that means is the effects of the storm, so the effects of space weather are generally at the poles. They're generally Antarctica and the Arctic. But in a storm, they come further down. So they might be impacting us here in Ireland, but South Africa is showing this is a huge storm because it's come to a mid-latitude, low-latitude kind of region. In terms of travel, you can see this solar radiation alert region here. So here's again a map of the world. These red areas are regions where you're not allowed to fly. So that is a huge swathe of the world. And so that's because of increased radiation exposure when you're at that higher altitude, because down here the atmosphere is protecting us. You go up a little bit further, there's a lot more chance of radiation. It means there's communication blackouts and issues with your GPS. Basically, planes can't fly in those regions. And for every flight that was rerouted, they estimated it could be 10 to 10,000 US dollars per flight. So again, that's annoying if you get stuck on holiday for one day, but that is costing the airlines and therefore the economy and therefore the price of your ticket quite a lot of money. But thankfully, we are best placed to know not to fly and not to risk the danger, but it's just costing us money. In terms of communication, HF radio had complete blackouts, some areas just little issues and some complete blackouts. We couldn't do offshore drilling operations were cancelled. So offshore drilling requires very precise GPS, and GPS is very strongly affected by space weather. So if you're in your car and it's sending you 100 meters in the wrong direction while you can see where you're going, that's okay. But if you're drilling and you can't see what you're doing, or you're landing a plane in fog, it's really important that your GPS is precise. And finally, some Earth orbiting satellites were damaged. Some of them they got back in a few hours, some of them completely wiped out. And that's a huge, huge economic loss. So what's really fun, or one of the really fun things about Halloween Storm is because we're in the space age, we have spacecraft throughout the solar system, so we can try and track it. Now, this is a nice slide I made, but it's important to note that the solar wind is not traveling out in a straight line through the solar system. It's going in more of a spiral. But we can see it in these different places. So we're going to have a look at what we saw. So it's not always pretty pictures when we're far out in the solar system. These days it is because we have fancier equipment, but back then not so much. So firstly, 400 kilometers above the Earth's surface in the International Space Station, astronauts had to seek shelter because that radiation from the storm was coming in. They have no atmosphere to protect them. That's really dangerous for them. So they have little lead-lined rooms they have to go and sit in until the storm passes. And a geomagnetic storm can last for maybe 2 days. So that's a really miserable, boring 2 days for them. We move slightly further out into the solar system, so 200 million kilometers from the sun. The storm took about 43 to 44 hours to get there. This is Mars Global Surveyor. So the effects of the solar storm lasted for about 40 hours at Mars. So again, we're talking about more than a day. Obviously, there were no humans at Mars, but we did see it in the instrument. Mars Global Surveyor saw a really high solar wind pressure. So that's like a big punch in the face kind of pressure. And another satellite, Mars Odyssey, had one of its instruments completely destroyed. And that's an instrument that's, loads of money's gone into, we've had to fly it all the way to Mars, and now it's broken because of space weather. So it just shows you can't beat nature sometimes. Nature often wins. Even further out in the solar system, near Jupiter, so now we are 800 million kilometers from the sun. I had some fun writing this talk, getting from really long numbers to words and numbers that make sense. So the Ulysses probe is actually a probe that some of my colleagues in DIAS use to look at Jupiter. If you look at this diagram here, so we are looking down on the solar system, the sun is in the middle. You can see Earth, you can see Mars. If we go out much further and round a bit, you can see Ulysses. So that's where Ulysses is. It's much further away from the sun, but it's still seeing the same event. That solar event is taking over the solar system, where it's being seen everywhere. And it saw the same particles, so not the exact same, Fred and Bob that hit the Earth, but from the same family of particles that we saw at Earth. And just to say, I have little nice pictures of the satellites here, but hopefully you worked that out. Then the Cassini spacecraft, 1.3 billion kilometers from the sun. It was on its way to Saturn, didn't quite make it there yet. We actually have one of the world-leading experts in Cassini and Saturn working at DIAS, Katrina Jackman. Now, not all of the instruments in Cassini were looking in the right way at the time when the storm passed, but one of the instruments saw the shocks that we see. So if you can think back to the river passing around the rock, when the river first impacts the rock, that is the shock. And it's the same for the solar wind in the solar system. So the shock, it's like the punch moment when someone hits you in the face, that initial, that's, hopefully no one's going to hit you in the face today, that is the shock. And that's what Cassini saw a couple of weeks after we saw them at Earth. And then finally, we have Voyager 2. So Voyager 1 and Voyager 2 were launched, and they are traveling far away. At this time, Voyager 2 was 10 billion kilometers from the sun, so beyond the planets in the outer solar system. And it saw the event, the Halloween storm, 180 days after the start of the event at the sun. So it took 180 days to get to Voyager 2. And by this time, you remember I said there were multiple things that came out of the sun. They had all kind of merged into one. So it's kind of like, if you're in this, dropping stones into the lake, and then eventually by the edge of the lake, it's all just one wave. That's kind of what's happening here. They're catching up and merging with each other. And then just for fun, not related to space weather, where is Voyager now? Because that's something that people always want to know, right? So here, it's not coming out very well on this TV. Maybe you can see it better here. Yeah, a little bit. So this is a schematic showing Voyager 1, not Voyager 2 that we talked about just now, looking back at the solar system. So you can see it's kind of, I find it kind of a little bit sad that it's looking back at us like that. And you can see a table here. I screenshotted this on Friday, so you can go on the NASA website and they will tell you exactly where Voyager 1 and Voyager 2 are right now. But on Friday, I don't know how to put that number into words, maybe 20 and then 9 other numbers, kilometers from the Earth. So that is something we launched in 1977. Still working today, still going, reliable old Voyager 1 and Voyager 2 out in the solar system. So, back to space weather. That was a fun interlude. Let's go back to the Halloween storm and talk about the aurora. So has anyone seen the aurora in real life? Yeah? Yeah, so I saw it the first time this year in the May storm. That's being called the Mother's Day storm because it was Mother's Day weekend in the States that weekend. But the Halloween storm was kind of one of the big precursors to that. So just let's talk about how aurora are formed before we look at the nice pictures. You actually see there's some aurora, well, there's one at the back there from our astrophotography competition. So here we have a coronal mass ejection coming out of the sun. Here's the Earth's magnetosphere that we talked about before. So the coronal mass ejection hits into the sun, hits into the Earth, sorry, and we have this cycling of magnetic field lines. You can see they're moving over. And then what you can see is you see the magnetic field, it undergoes magnetic reconnection here, and the particles form on the lines, they get pinged down. So magnetic field lines, I remember my hairband this time, they're like elastic bands. So what's happening in the tail there, in the sort of right-hand side of the magnetic field's pinging like that And the particles, if you imagine beads on this, are getting pinged into the planet. So we can watch that again. Just skip a bit. So you can see the particles, the cloud here is kind of forming on the field lines. Those are particles from a number of different sources, and the magnetic field is going to ping in a moment and accelerate them down the field line to impact into the Earth's atmosphere. And you see these rings here, those are the auroral ovals, the rings of aurora. They're like crowns on the north and south magnetic pole. So one of the things that we generally associate this with is a phenomenon called substorms. They're much quicker, more dramatic than geomagnetic storms that we talked about before. So geomagnetic storms, a couple of days, substorms, a couple of hours. And what they're doing is this cloud of particles, as I said before, is being propelled down the field lines. So these are ions and electrons, again, and they're raining down on the Earth's upper atmosphere. And that generates the aurora. So what's happening is the charged particles, they're buffeting the Earth's atmosphere. So they're having one-on-one collisions. So we have charged particle comes in, collides one-on-one with a neutral particle in the Earth's atmosphere. So that's oxygen and nitrogen mostly. And then these neutrals, they have all that energy, they just shine out in terms of visible light. And here we've got a nice GIF of the aurora over some nice icy region. So this is looking down on the aurora from space. This is looking from the International Space Station. You can see that there's actually lots of fine structure here. Like it's not just one donut. There's lots of like small, intricate structure that actually we have known about probably before we knew it was a ring because of being able to see it for societies that lived in those kind of regions. So the brightness and colors are changing as well. So most often the aurora is green. It can be red and it's very rarely blue. So when I saw it in May, it was kind of purpley as well, which is super rare. But it was right overhead of Ireland in May. We also see it in ultraviolet and infrared. So ultraviolet is your sort of your invisible ink pen, and infrared is your night vision goggles. So then in terms of seeing it locally, so these are from that May storm I mentioned. So we have photos from my colleagues here. So this was taken on Hoath, and this was taken in Meath. So you can see really beautiful auroral images taken locally. And then on your way out, on the railings, there's a few more images that have been taken in Ireland as well. So back to the Halloween storm. Not everybody had a smartphone in 2003, so we don't have as many images. But I've got one here from Houston in Texas. So again, that's demonstrating that the aurora, really low latitude, coming all the way down to Texas. And then we have a satellite image here, so they've kind of superimposed it on a map, because you can't see all these borders in space. But here you can see the auroral oval. You can see city lights. Obviously, we're over here. There's a tiny little bright patch for Dublin. And this is taken by the DMSP, which is an American military satellite. So those are some of our auroral images from the Halloween storm. But it was seen, it just wasn't captured as much as the storm this year because obviously cameras are much more available now. And then this is another one from space. So this is from the IMAGE satellite. And I'm going to play it again. It's kind of short. And you can see this is looking at the southern magnetic pole. And you can see it's making a ring. And it's bright, and it's dramatic, and it's moving around. It's not static. And that, all those bright patches, those are, when we look at that frame by frame, that's really demonstrating to us that it's a geomagnetic storm. Those are features that we know and we expect. And this IMAGE satellite was really great for capturing those. Unfortunately, it is no longer with us. So, I always like to finish up my talk with talking about how you can see the aurora. So there's three things you kind of need to see the aurora on the island of Ireland. So does anyone want to take a guess? I've given you one of the answers in the talk already, which is you need a storm. So I think that's the first one. So we need disturbed geomagnetic conditions. Now there's a number of ways you can find out about this. Sometimes it's on the national news, sometimes it's not. There's this Twitter account here I would recommend. It's called Aurora Watch UK. Obviously, we are not in the UK, but it is the nearest one to us geographically that is run by scientists. I think there is also an Aurora Watch Ireland. I don't know that one so well, but it's not. This is the one that's run by a university. So that's the number one thing. So you can follow this Twitter account. You can follow, we have magnetometers in Ireland called Maggie, and they demonstrate, but they don't tweet, unfortunately, not yet. Anyone want to guess 2 other things you need to see the aurora? It is not a trick question.
Clear skies.
Clear skies, and some of you say something else?
The right polarity.
The right polarity, no. Yeah, so, well, okay, I'm just going to tell you guys. Maybe, these are my 3 things. You need low light pollution, so you need to be somewhere rural, because it's not as bright as the street lights, generally speaking. So go to Kerry, go to, I saw them on Howth, but if you want to be on the northern side of the Howth Peninsula, looking north so you don't have the city lights, that's my recommendation. There was tons of people there. It was great. And then you need clear skies. So that's our biggest mitigating factor, I think, in this country, that you can't count on the weather. So those are your 3 things. You need to know when it's happening, you need your low light pollution, and you need your clear skies. So that kind of wraps up my talk. I have my QR code here again for dunsink.dias.ie, and you can follow us on social media. But yeah, I will happily take any questions you have. Yeah. Yeah. So the short answer is no. So in terms of space weather prediction, at the moment, we can look at the sun, we can see the event, and then we can say it's going to happen in sometime in the next week. In terms of predicting and saying, okay, there's going to be one, 3 weeks tomorrow, we don't know what the sun's going to do. So that's a huge area of science, is trying to be able to look at the sun and know what it's going to do in a week from now. But we do know some kind of trends. So the sun goes through an 11-year cycle. So at the moment, we're at solar maximum, and that's why we had this really dramatic, really cool storm in May. And then, in a while from now, we'll be at solar minimum, less storms. So we know to expect more and more dramatic storms right now, but we don't know if there's going to be one next week, if that makes sense. And then the other issue with predicting is, okay, we know the sun's going to do something, we don't know exactly what it's going to do to the Earth as well. We know a general idea, but the precision we don't have. Yeah?
Thank you. Great talk. Wonderful.
Thank you.
Just to know, this might be a very basic question, as well as knocking out all the equipment, do these storms actually affect Earth's weather as such?
So it's not on a large scale. So I like to think the atmosphere is like a trifle, right? So if you think you have your custard and your cream, the custard being the troposphere, where we are, where the rain happens, and then the cream is the layer of the atmosphere where space weather is happening. If you think about the trifle, until you put the spoon in, they're not mixing. There's a little bit of mixing, but it's minor compared to everything else. So it's a very, very small effect that we wouldn't need to consider. Yeah.
Thank you.
Thanks. That was really interesting. Just on the polarity, the CME, if the polarity is north, and conventionally we talk about the north magnetic pole of the Earth, even though it is a south, but conventionally, like poles repel each other. So if the CME is magnetically north polarized, it would be attracted to the Earth's south pole and vice versa. So, that's what I was talking about, okay, the polarity.
Right. Yeah, so I see what you mean. So if we go back to, if I have a picture of the Earth's magnetic field, way back. So the direction of the solar magnetic field when it meets the Earth's magnetic field is important.
Yeah.
So it's less of this is really far back. Okay, so if you see the magnetic field lines, if you can see them in this one here, they're pointing up. So when the sun comes to meet the Earth's magnetic field, if it's also, the sun's magnetic field is also pointing up, not very much happens. If it's pointing directly opposite, so we have the sun going down and the Earth going up like that, then what happens is much more dramatic, because they kind of, it's again, magnetic reconnection, we sort of touched on that, but it means that you end up with this direct connection between the sun's magnetic field and the Earth's magnetic field, and there's a lot of energy transfer. So that does make a difference, yeah. I wasn't sure that I didn't realize that's what you meant.
Yeah.
So, sorry.
So, yeah, that leads me on to the question I was going to ask. The 2003 event, there was a fair amount of damage done, you were saying, in transformers in South Africa. So that affected both hemispheres. And I think what happened in that case is that the leading edge of the CME was polarized in one direction, and the bit that came after was polarized in the other direction, and that's how it affected both hemispheres.
Yeah.
The same thing happened in the May event here. The start of that event was favorable for us in the northern hemisphere, and we knew that more of the CME was still coming, and so there was hope that there'd be activity the second night, but actually the polarity changed and people in the southern hemisphere got a better view on the second night. Some fantastic photographs taken by people I know in New South Wales, which isn't a particularly high latitude in the southern hemisphere.
Yeah. So seeing the aurora in Australia again is a lucky kind of like it's a big geomagnetic storm event for the aurora to be going, in that case, up, I guess, depending on your perspective, to Australia. Yeah.
Thanks very much.
Vi har lært rektorer shinge hiatach agus vi ga hel hiatach fashion. Your Irish is great. That was a great lecture too.
Okay,
Thank you very much indeed. You did a great job. Very well done indeed.
Biogonin.
Yeah, that's okay, yeah. Back to astronomy, as I said. Just want to ask something from the theory that you covered. When the magnetic fields flip, what effect will that have upon the aurora? As I said, it hits the Earth, as is predicted in the future as well. And as I said, how could we predict, as I said, if magnetic storms are going to become more or less intense if the Earth's poles flip, as I said, within the near future, as it's commonly predicted they're going to be?
Yeah, so just to sort of build on that, so there's a thought that we're seeing that a bit of a decrease in the strength of the Earth's magnetic field, and we think that means it's going to flip. So the bar magnet flips upside down. What we have in that situation is we have these magnetic field lines pointing the opposite way. Now, that flipping period is going to be a really interesting time for people in my field. In terms of what we're going to see in terms of aurora and space weather, I think it's going to be pretty much the same, kind of equal and opposite. So what I said about when the sun's magnetic field is this way, the Earth's magnetic field is this way, we just need it to be the opposite situation. And in terms of the average solar magnetic field that's coming out, we're going to see it roughly the same amount. So it's kind of equal and opposite, if that makes sense. But a really interesting time for people in my field, if it happens in my lifetime, I don't know, when this magnetic field flips over. Yeah.
Hi, great presentation. I've read somewhere that every CME is, so there are X-class flares and M-class flares, and not every flare will have an aurora, or every CME will have an aurora. Can you just expand a bit on that?
Yeah, so every flare, every CME is completely unique, and therefore when they come to meet the Earth's magnetic field, they interact in a different way. So the thing I said about the opposing magnetic fields is really important. That makes a huge difference. If the magnetic fields are going the same way, sometimes very, very little happens. So the flares can also have a really direct and really immediate effect on the Earth's ionosphere and really change. That's the upper layer of the Earth's atmosphere, the cream in the trifle, as I said earlier. But it's kind of a thing of nature. You know, everything in nature is completely unique, and therefore the response is completely unique. If it was a perfect laboratory, we could repeat the event and we would see the exact same thing. But space, which is my laboratory, is changing all the time. It's never, the same thing never happens twice. In the same way that you never get the exact same tree growing, no two cats are identical, and things like that. Like it's just nature, it's always different, because there's so many variables. You know, which way is the Earth's tilt facing? where are we, rotating? Where are we in the Earth's orbit? What is the sun doing? Which part of the solar cycle? There's so many variables. It's different every single time.
Right. And is it also that the radiation that the particles that are erupted or they come from the sun, sometimes they hit or miss the Earth as well?
Yeah, they can do so. The way, so it's not, when it's coming out of the solar system, it's not coming straight out in a line, it's kind of spiraling around like this. So the spiral doesn't always hit the Earth. So there's a ton of events that the sun do that they don't hit us at all. It's the ones when they come and they hit us directly on, that's when we get the big space weather. So they can completely miss the Earth, yeah.
All right, thank you.
Which is overall best for us.
All right, thank you.
So you mentioned that governments are now beginning to prepare themselves more for space weather. Is there anything that can be done on a large scale, or is it just kind of shielding critical pieces of technology individually, and that's kind of the best that we can do?
Yeah, so I mean, it is pretty much that. So in terms of preparing yourself and trying to stop bad things happening from space weather, that's the kind of thing that's happened in my lifetime, the governments have started to do. So generally, when we're thinking about the power systems, if you imagine electric current, or between two pylons, for example, if they leave that closed and we get loads of space weather induced current in that length of wire, my arms, then it's going to overload. So what they tend to do is open the doors and let it all swirl around. That's the best defense we have. And then eventually it dissipates, the event ends, everything's cool. If they leave it closed, then you get the fuses blowing and the switches tripping and, parts get broken. And then you have to bring the new parts and fix it. And that's when you get the power cut. In terms of spacecraft, what they will do is put them in a safety mode. So they might, if they have a particle instrument that we would use in my field to detect these events, they'll, close the doors, because if those particles come in, they'll wreck the instrument, like happened to one of the Mars things. So it's these kind of doing our best to protect things. But in terms of if we had that Carrington event today, I think we would lose a great deal of technology, particularly space-based technology. So in terms of the power line stuff, it's mostly a big deal with the really long power lines in North America. We're actually kind of not so bad off with that here because we're a much smaller island. And trying to understand and predict what's happening specifically to Ireland is something that we do at DIAS. Here we use our Irish instruments to understand that. But yeah, it's sort of it's not something we've perfected as a society yet. But it's also something that it depends how much your government cares about it. So you need your government to care about it. That's the end of my soapbox for today.
Thanks. We can also get aurora when there are coronal holes. Do you know much about the mechanism at which that happens, that basically allows the magnetic field to stream out uninterrupted? Does that come at roughly the same rate as the CMEs and the flares?
Yeah, so I mean, I wouldn't be an expert in coronal holes. My hand-wavy explanation of a coronal hole is that it's, I guess the reason we use hole is a lot is coming out a lot faster than normal. So it's different to a CME in that a CME is a burst. It's like a punch. A coronal hole is more of a long thing. I don't know what that turns into by the time it gets to the Earth. It could be we have something called a co-rotating interaction region that can have similar effects. I mean, the short answer is I don't know. Coronal holes, it's not. I will go home and look that up. Well, tomorrow. Look that up. Yeah.
Okay, thanks.
Hi there. I'll try articulate this.
Yeah.
But are there any other perhaps older suns in the universe that are being studied to see as to what stages they're at that our sun might follow onto?
Yeah. So that is far outside of what I know about science. But in terms of my research, what I can tell you in terms of space weather, like exoplanetary space weather, thinking about planets outside our solar system, we do study exoplanetary space weather, and the best way that we can do that is looking at planetary radio emissions. So in our solar system, the Earth, Jupiter, Saturn, Uranus, and Neptune are natural radio emitters. So you can't see this from the ground, but if you go into space, you can hear their radio signals, obviously not with your human ears. What we can see, if we look for those signals in other places in the universe, we can see other stars doing the same space weather effects to other planets, which we call exoplanets, planets outside of our solar system. So exoplanetary space weather is kind of an emerging field. It's obviously much harder to see things that far away. But those radio emissions that we study at DIAS, that is the best way we can look at space weather in other solar systems and from other stars. But there are almost, in fact, I'm going to say definitely, other stars out there doing the same thing. Not the exact same thing, because we said about the nature thing, it's different every time, but they're doing the same thing. They're causing aurora, they are compressing the magnetic field, all these kinds of things, yeah. So I'm going to go back to my slide with the QR code right at the end. So yeah, do come see us at Dunsink Observatory. It is quite competitive to get tickets, so you've got to be there when the Eventbrite opens. But it's a fun night. There's talks, there's telescopes. If you've got kids, it's kid-friendly. We have stickers, we have a treasure hunt for them. And we're developing a new set of resources for visually impaired people at the moment as well. So we're going to have lots more things that don't say, please do not touch, which is great.